A proportion is a fundamental mathematical concept that shows when two ratios are equal to each other. Understanding proportions is essential for solving many real-world problems. A proportion is an equation that states that two ratios are equal. It shows the equivalence of two fractions or ratios, establishing a mathematical relationship between four quantities. Proportions can be written in two main formats. The fraction format shows a over b equals c over d. The ratio format uses colons and shows a to b as c to d. Let's work through a practical example to see how proportions work. If the ratio of apples to oranges is 3 to 5, and you have 6 apples, how many oranges should you have? We can set up a proportion using the known ratio and the given information. 3 apples to 5 oranges equals 6 apples to x oranges, where x is the unknown number of oranges we need to find. To solve this proportion, we can use cross multiplication. We multiply the numerator of the first fraction by the denominator of the second fraction and set it equal to the denominator of the first fraction times the numerator of the second fraction. Simplifying the right side, we get 3x equals 30. Dividing both sides by 3 gives us x equals 10. Therefore, you should have 10 oranges. Let's verify our answer by checking if the ratios are equivalent. 3 to 5 should equal 6 to 10. Cross-multiplying, 3 times 10 equals 30, and 5 times 6 also equals 30. Since both products are equal, our answer is correct. Proportions are essential tools in mathematics and everyday life. They are used for scaling recipes up or down, converting between different units of measurement, and solving countless real-world problems involving equivalent relationships. Understanding proportions provides the foundation for more advanced mathematical concepts and practical problem-solving skills that you'll use throughout your mathematical journey. Proportions have several fundamental properties that make them incredibly powerful tools for solving mathematical problems. Understanding these properties allows us to manipulate equations and find unknown values efficiently. We begin with a basic proportion where a over b equals c over d. From this single equation, we can derive several important properties that help us solve complex problems. The first property, called alternando, states that if a over b equals c over d, then a over c equals b over d. This means we can rearrange the terms by taking the first terms together and the second terms together. The second property, invertendo, allows us to flip both fractions. If a over b equals c over d, then b over a equals d over c. This is like turning both fractions upside down simultaneously. The most important property is cross-multiplication. When a over b equals c over d, we can multiply diagonally. A times d equals b times c. This is called the product of means equals the product of extremes, and it's the foundation for solving most proportion problems. These properties have many practical applications. They allow us to isolate unknown variables, simplify complex proportions, verify our solutions, and transform equations to make them easier to solve. For example, to find x when 3 over x equals 6 over 8, we use cross-multiplication. 3 times 8 equals 6 times x, giving us 24 equals 6x, so x equals 4. The properties make this solution straightforward and reliable. Understanding these key properties of proportions provides the foundation for solving any proportion problem efficiently and accurately. They are essential tools that transform complex relationships into manageable equations. Recipe scaling is one of the most practical applications of proportions in everyday life. When cooking or baking, maintaining the correct ratios between ingredients is crucial for achieving the desired taste, texture, and consistency. Consider this simple recipe that calls for 2 cups of flour and 1 cup of sugar. The ratio of flour to sugar is 2 to 1, which means for every 2 parts flour, we need 1 part sugar. This ratio of 2 to 1 is the key relationship we must maintain when scaling the recipe. Whether we make more or less, this proportion must stay constant. Now suppose we want to double this recipe to serve more people. We need to scale up all ingredients proportionally while maintaining the same ratio. To double the recipe, we know the sugar will increase from 1 cup to 2 cups. We need to find how much flour is required. We set up a proportion where x represents the unknown amount of flour. Now we solve this proportion step by step using cross-multiplication. This method ensures we maintain the exact same ratio in our scaled recipe. We cross-multiply x times 1 equals 2 times 2. This gives us x equals 4. Therefore, we need 4 cups of flour for the doubled recipe. Let's verify our answer by comparing the original recipe with the doubled recipe to confirm the ratios are maintained. The original recipe has 2 cups flour and 1 cup sugar with a ratio of 2 to 1. The doubled recipe has 4 cups flour and 2 cups sugar, which simplifies to the same 2 to 1 ratio. The proportion is perfectly maintained. This same principle applies to any scaling factor. Whether you want to triple the recipe, make half the recipe, or scale by any other factor, you use proportions to maintain the correct ingredient relationships. Understanding recipe scaling through proportions ensures consistent results in cooking and baking. This mathematical approach guarantees that flavors, textures, and cooking times remain predictable, regardless of batch size. In this section, we'll explore how proportions help us solve real-world problems involving distance and speed. Understanding this relationship is crucial for many practical applications. Here's our problem. A car travels 120 miles in 2 hours at a constant speed. We need to find how far it will travel in 5 hours at the same speed. Let's visualize this problem. The car starts at position 0 and travels 120 miles in 2 hours at a constant speed. To solve this problem, we need to set up a proportion. Since the car travels at constant speed, the ratio of distance to time remains the same for any time period. We set up our proportion with 120 miles over 2 hours equals x miles over 5 hours, where x is the unknown distance we want to find. Step 1, we cross-multiply to solve for x. This gives us 120 times 5 equals x times 2. Step 2, we calculate 120 times 5, which equals 600. So we have 600 equals 2x. Step 3, we divide both sides by 2 to solve for x. 600 divided by 2 equals 300 miles. Let's verify our answer. The car's speed is 120 miles divided by 2 hours, which equals 60 miles per hour. At this speed, in 5 hours, the car would travel 60 times 5, which is 300 miles. Both ratios equal 60 miles per hour, confirming our answer is correct. Here are the key insights from this problem. Constant speed creates proportional relationships between distance and time. The ratios of distance to time remain equal at constant speed. Cross-multiplication efficiently solves proportion equations, and always verify your answers using the original relationship to ensure accuracy. This example demonstrates how proportions are essential tools for solving distance and speed problems in real-world situations. The mathematical relationship allows us to predict outcomes and make calculations with confidence. In inverse proportion problems, we work with quantities where one increases as the other decreases, but their product always remains constant. This relationship appears frequently in real-world scenarios involving time, speed, workers, and resources. The fundamental principle of inverse proportion is that the product of two related quantities remains constant. When we have two situations with inversely proportional quantities, we can write x1 times y1 equals x2 times y2. Here's a classic inverse proportion problem. If 4 workers can complete a task in 6 hours, how long will it take 8 workers to complete the same task? More workers means less time needed. We can visualize this problem. On the left, we have 4 workers taking 6 hours. On the right, we have 8 workers, and we need to find how many hours they'll take. Now let's solve this step by step. First, we identify that workers and time have an inverse relationship. As the number of workers increases, the time decreases, but their product remains constant. Step 2, we set up the equation using the constant product principle. 4 workers times 6 hours equals 8 workers times x hours, where x is what we're solving for. Step 3, we calculate the constant by multiplying 4 workers times 6 hours, which equals 24. Step 4, now we solve for x. We have 24 equals 8 times, so x equals 24 divided by 8, which equals 3 hours. Therefore, 8 workers can complete the same task in 3 hours. Notice how doubling the number of workers halved the time required, which is exactly what we expect in an inverse proportion. Here's another example to reinforce the concept. A car traveling at 60 miles per hour takes 4 hours for a journey. How long would the same journey take at 80 miles per hour? Using the same method, 60 times 4 equals 80 times x. This gives us 240 equals 80x, so x equals 3 hours. Higher speed means less time needed. Here's the general method for solving inverse proportion problems. First, identify that the quantities are inversely proportional. Then, set up the equation using the constant product principle. Calculate the constant, solve for the unknown, and always check that your answer makes logical sense. Remember, in inverse proportion problems, when one quantity increases, the other must decrease proportionally so that their product remains constant. This relationship is fundamental to solving these types of problems correctly. When working with ratios and proportions, students often make several common mistakes that can lead to incorrect answers. Understanding these pitfalls will help you avoid them and solve problems more accurately. The first major mistake is confusing direct and inverse proportion. In direct proportion, both quantities change in the same direction. When one increases, the other increases. In inverse proportion, they change in opposite directions. Here's a common error: thinking that more workers means more time. This is wrong because workers and time have an inverse relationship. More workers actually means less time needed to complete the same job. Another critical mistake is comparing quantities with different units. Ratios can only compare quantities that have the same units or are dimensionless. You cannot directly compare 2 meters to 50 centimeters in a ratio. First, convert to the same units. 2 meters equals 200 centimeters, giving us a ratio of 200 to 50, which simplifies to 4 to 1. A fundamental error is thinking additively instead of multiplicatively. Proportions involve multiplicative relationships, not additive ones. Students often think, if 3 apples cost $6, then 5 apples cost 6 plus 2 equals $8. This additive thinking is incorrect. The correct approach uses proportional reasoning. 3 apples to $6 equals 5 apples to X dollars, giving us $10. Cross multiplication is powerful, but students often set up the proportion incorrectly, leading to wrong answers even when the calculation is correct. The key is keeping the same units in the same positions. Pencils should be compared to pencils and dollars to dollars. The wrong setup mixes the positions, leading to an incorrect answer. To avoid these common mistakes, first, always identify whether you have direct or inverse proportion. Second, ensure all units are consistent. Third, think multiplicatively about relationships. Fourth, keep the same units in the same positions when setting up proportions. Finally, always double-check your setup before calculating. By being aware of these common pitfalls and following these prevention strategies, you can solve ratio and proportion problems more accurately and confidently. Before solving proportion problems, we should always look for opportunities to simplify our ratios. Simplifying ratios makes calculations easier, reduces the chance of errors, and helps us see relationships more clearly. Simplifying a ratio means reducing it to its lowest terms by dividing both parts by their greatest common divisor. This creates an equivalent ratio with smaller, more manageable numbers. Let's work through the classic example of simplifying 12 to 18. First, we need to find the greatest common divisor of 12 and 18. To find the greatest common divisor, we can list the factors of each number. The factors of 12 are 1, 2, 3, 4, 6, and 12. The factors of 18 are 1, 2, 3, 6, 9, and 18. The common factors are 1, 2, 3, and 6. The greatest of these is 6, so our greatest common divisor is 6. Now we divide both parts of our ratio by 6. 12 divided by 6 equals 2, and 18 divided by 6 equals 3. So 12 to 18 simplifies to 2 to 3. Why is simplifying so important? Simplified ratios are much easier to work with in calculations. They reduce the chance of arithmetic errors and make patterns more visible. Let's see this in action. Let's try a more challenging example. Suppose we have the ratio 24 to 36. We need to find the greatest common divisor of these larger numbers. For larger numbers, we can use the division method to find the greatest common divisor more efficiently. We divide the larger number by the smaller number and continue with the remainders. Now we divide both parts by 12. 24 divided by 12 equals 2, and 36 divided by 12 equals 3. So 24 to 36 also simplifies to 2 to 3. Simplifying becomes especially powerful when working with proportions. Consider this proportion. 12 over 18 equals x over 9. Instead of working with these larger numbers, we can first simplify. We already know that 12 to 18 simplifies to 2 to 3, so our proportion becomes 2 over 3 equals x over 9. This is much easier to solve. Now we can easily see that x equals 6, since 2 times 3 equals 6, and 3 times 3 equals 9. The simplified form made this relationship immediately clear. Remember these key points about simplifying ratios and proportions. Always look for common factors before solving. Use the greatest common divisor to reduce ratios to their simplest form. Simplified ratios make calculations faster and more accurate. This fundamental skill will serve you well in all proportion problems. Proportional reasoning is essential in geometry, particularly when working with similar figures. Similar triangles have corresponding sides that are in proportion, allowing us to solve for unknown measurements. Here we have two similar triangles. Triangle ABC is larger, and triangle DEF is smaller but has the same shape. Notice that the angles are identical, but the sides are proportionally different. We know some measurements. Triangle ABC has a base of 3 units and height of 2 units. Triangle DEF has a base of 1.8 units and height of 1.2 units. We need to find the length of side EF, which we'll call x. In similar triangles, corresponding sides are in proportion. This means the ratio of any two corresponding sides is the same for all pairs of corresponding sides. Let's substitute our known values. We have 3 over 1.8 equals 2 over 1.2 equals BC over x. First, let's verify that our known ratios are equal. Let's calculate these ratios. 3 divided by 1.8 equals 1.67, and 2 divided by 1.2 also equals 1.67. Since these ratios are equal, we confirm the triangles are similar. First, we need to find the length of BC. Using the Pythagorean theorem, BC squared equals AB squared plus AC squared. That's 3 squared plus 2 squared, which equals 9 plus 4 equals 13. So BC equals the square root of 13, approximately 3.61. Now we can solve for x. We know that 3.61 over x equals 1.67. Cross-multiplying and solving, x equals 3.61 divided by 1.67, which is approximately 2.16. We can verify our answer by checking that all ratios equal 1.67. This confirms that our solution is correct and the triangles maintain their proportional relationship. Proportional reasoning in geometry relies on the fact that similar figures have corresponding sides in proportion. By setting up ratios and solving proportions, we can find unknown measurements in geometric figures. This principle is fundamental to scaling, similarity, and many real-world applications. Financial decision-making relies heavily on proportional reasoning through various ratios that help us analyze and compare financial data. These ratios provide crucial insights for investors, lenders, and individuals managing their finances. The debt-to-income ratio is one of the most important financial ratios used by lenders to assess creditworthiness. This ratio compares your total monthly debt payments to your gross monthly income, expressed as a percentage. Let's examine a practical example. Sarah earns $4,000 per month and has total monthly debt payments of $1,200. Her debt-to-income ratio would be 30%. The calculation shows that Sarah's debt-to-income ratio is 30%. Most lenders prefer to see a DTI ratio below 36% for total debt, with housing costs not exceeding 28% of income. Another crucial financial ratio is the price-to-earnings ratio, commonly known as the PE ratio. This ratio is fundamental in stock valuation and investment analysis. The PE ratio tells investors how much they're paying for each dollar of a company's earnings. A higher PE ratio might indicate that investors expect higher earnings growth in the future, while a lower PE ratio might suggest the stock is undervalued or the company is experiencing difficulties. In this comparison, Company A has a PE ratio of 20, meaning investors pay $20 for every dollar of earnings. Company B has a PE ratio of 30, indicating investors are willing to pay more per dollar of earnings, possibly expecting higher growth. Financial analysis involves many other important ratios that use proportional reasoning. These include liquidity ratios, profitability ratios, and efficiency ratios, each providing different insights into financial health. Understanding these financial ratios and their proportional relationships is essential for making informed investment decisions, assessing creditworthiness, and evaluating business performance. Each ratio provides a different lens through which to view financial health and potential. Understanding ratios and proportions goes far beyond simply memorizing procedures and formulas. True mathematical mastery comes from developing conceptual understanding, knowing not just how to solve problems, but why the methods work. There are two fundamentally different approaches to learning mathematics. The procedural approach focuses on memorizing steps and algorithms, while the conceptual approach emphasizes understanding relationships and reasoning. Consider cross multiplication, a common procedure for solving proportions. A student using the procedural approach simply memorizes the steps, cross multiply, then divide. But a student with conceptual understanding knows why this works. The conceptual approach recognizes that cross multiplication works because we're finding equivalent fractions. When we multiply both sides by the same value, we maintain the equality while eliminating fractions. Conceptual understanding provides several crucial advantages. It enables students to adapt their knowledge to new and unfamiliar problems, rather than being limited to situations that exactly match memorized procedures. Think of conceptual understanding as building a strong mathematical foundation. Each concept connects to and supports others, creating a robust structure that can support advanced mathematical thinking. When students truly understand the conceptual foundations of ratios and proportions, they develop mathematical reasoning skills that extend far beyond these specific topics. This deep understanding becomes the basis for success in algebra, geometry, calculus, and beyond.